Hi everyone, welcome to the RISC-V Summit Keynote panel. And today we're going to have a hopefully interesting discussion around how open source technologies work well for machine learning in IoT, how it all combines with RISC-V, and some real-world examples of this happening. Firstly, let me introduce my panelists today. First, we have Kate Stewart, who's Senior Director of Strategic Programs at Linux Foundation. She's representing the Zephyr project, and she's very, very involved in this ecosystem. Next up is Brian Faith, who's CEO of Quicklogic, an FPGA and eFPGA company that's doing some really interesting stuff in this space right now and aligning very strongly around open source software and hardware. And lastly, we have Tim Ansel from Google, who somehow ends up being at the nexus of many of these projects here. So very good to have him talk to us about it. Okay, so let's start and jump to the first round of questions. Since we're focusing today around machine learning in IoT, where RISC-V is indeed being pretty successful, I wanted to first ask Kate, why is Zephyr such a good fit for RISC-V?
Well, Zephyr is a very small RTOS that is useful when Linux just doesn't fit. It's got a lot of Linux influences in it though, kconfig, device tree. So most of the embedded Linux developers are actually pretty familiar with this, which gives us a really nice leg up. It's got a very clean code base and an active developer community, and targets 32 and 64 bits. So there's pretty good support for those architectures in there. It doesn't have anything really for 8 though. So there's none of that. There's not a lot of that history there, but the code base is pretty clean. It's also an open governance project. Basically, it's not controlled by any one company. We have a TSC, and goes into the code base, gets decided by the TSC. So if you've been used to working in Linux, Zephyr is a pretty easy transition.
Yeah, thanks. That makes total sense. So switching to Brian, perhaps, Quicklogic working with FPGAs and eFPGA technology. So what do you bring into the IoT space? How do you see yourselves fit into that space?
Well, a lot of people think of FPGAs as really big, high-performance beasts. They can actually be on the other end of the spectrum, very low power and cost and space efficient. And so we're focused on that end of the spectrum, which really lends itself well to IoT, particularly battery-powered IoT. One of the other things that we're doing is integrating that programmable logic into higher complexity devices like microcontrollers. And we have a really low power one based on Cortex-M4 today. Our next generation is going to be moving that into the RISC-V domain, which we're really excited about. And some of the neat things you can do with FPGAs is you can adapt the platform as the market moves or as your needs move without going back and changing the base silicon. So it lends itself to sort of agile hardware development, which is, I think, a really neat technology for this particular space.
Okay, so Brian, how does this relate to machine learning then? What's the role that FPGAs might play in machine learning?
That's a great question. I think a lot of people think of FPGAs and machine learning more for data center applications, but you can actually do it again at the other end of the spectrum where the sensors are. And some of the things that we're seeing really useful use cases for with our embedded FPGA is to offload some of the inner loop of processing, like for convolutions, partition between FPGA and embedded processors. And in fact, we can see quantifiable evidence, in fact, of 5x performance increase at least, perhaps 5x power reduction at least, when doing these types of things. You can imagine what that enables for use cases when you are powering things with a battery and expect long battery life from that.
So I assume you mean that FPGAs have a pretty kind of big role to play in the future for machine learning.
They have a huge role to play in the future, as long as we can make it easy for everybody to use, which I think is one of the points of this panel.
So actually, perhaps I'll switch that to Kate then. What does Zephyr kind of do for ML? How can Zephyr be used in the machine learning space?
Well, there's actually been a lot of integration that's been going on now between the tiny Antmicro stuff and Zephyr. And so Michael's company, your company, has been doing a lot of the great work in actually making this together with Pete Walton. There's a lot we're going to need in ML going forward. And then, when we talk to the sensors, when we're sort of setting up cameras, things like that, Zephyr can provide a good base for the drivers and easy to interface so that people can build upon that.
Okay, awesome. Tim, we actually haven't asked you a question yet, and I wanted to kind of kind of gears a little bit into seeing how, things like RISC-V, Zephyr, FPGAs can work together and to achieve aims in this space. So perhaps can you tell us a little bit about why you care about this particular space, and why do you invest in so many technologies and frameworks there?
Sure. So generally, people consider FPGAs a quite hard technology to get into, and like it's even harder than embedded, which people tend to think is hard itself. And so what a lot of things I'm focused on is making that easier. And one of the ways you can make FPGA development easier is starting by treating it like a embedded microcontroller system. And once you start treating it like an embedded microcontroller system, which you just happen to have the source code for the complete CPU, then you're going to start needing things like operating systems and drivers. And once you get to that, things like Zephyr start making sense, especially because you don't want your CPU to take up significant resources. You're generally focused as well on smaller CPUs with fairly restrictive memory. And so things like Zephyr make a lot of sense there because it's a small system.
Yeah, okay. So actually that was my next question to Kate, more or less, like how can Zephyr be used for FPGAs effectively? How has it been used in the past? And what are you seeing in Zephyr's future to enable that use case?
Well, Zephyr's actually was used initially, I think, from RISC-V before even Linux got running on it, in the sense that it was a good starting point because it required few of the system resources to be programmed. And we've seen other architectures use it on their way to using Linux.
Right, could you perhaps tell us a little bit about your Nextgen platform? I mean, you mentioned this as part of your previous answer, but I wanted to kind of poke you a little bit around this new platform. I've heard it's going to combine RISC-V and FPGA Fabric. That sounds pretty exciting. So how's this also related to open source tooling and machine learning?
Yeah, so we're really excited about where we're headed with this new platform. I think to put it in context, we're doing things the way everybody's done it. We used an ARM core, we used our embedded FPGA, we used proprietary tools for that for our previous generation, kind of sitting on the sidelines waiting for when we thought everything was ready to be used in a product that we could actually commit to our customers. And we're at that point now. We feel like there is this convergence where RISC-V and the tool ecosystem around that is ready for prime time. We've always believed in our embedded FPGA ready for prime time from a silicon point of view. And we're convinced recently through our announcement with moving to TensorFlow and Renode and Zephyr that all of the open source tools are now ready for prime time as well. So we're sort of converging all of that into our next generation platform. A lot of that is largely based on work that we did with ETH and Zurich about 1.5 years ago, taking the RISC-V core from them and embedded FPGA and doing a test chip based on that. That's actually led to a lot of the research that we did to see that, quantifiably, yes, there is a lot of value to offloading software from RISC-V processors to embedded FPGA. And so all of this has converged. We're working on this with a few different companies right now, and hopefully we'll be able to release more details on that in 2021.
Incredible. Okay, thanks. Over to Tim now. I know that you're betting very strongly on open source, and generally speaking, using open source technology to help kind of develop hardware and software together to really innovate in machine learning. Can you perhaps tell us a little bit more about how open source helps you to effectively go very fast in this fast-changing space?
So when you're doing anything that is pushing the boundaries or doing something new, you're going to run into bugs because nobody's done this before and you're using it in a different way. You're probably exercising new code paths, new interactions, all these type of things. And every piece of software has bugs in it. And so you're going to hit these bugs. And being able to fix these problems quickly and within and unblock yourself and move forward is really important. You don't want to have to be dependent on waiting for other people to solve your problem for you. And particularly when you're in a space nobody else is in, nobody else is really able to necessarily understand why you're doing something a certain way. And so it's probably not incentivized to solve your problems either. And so controlling your own destiny and being able to modify your tools, improve your tools, is a really important part of being able to innovate. And so that's kind of why open source is so important in these cutting edge fields. It also allows you to build on top of other people's work and to collaborate with them without having to deal with lawyers, NDAs, all these other things that tend to slow down engineering development. And especially when you're doing something new, you might change direction extremely quickly, and who you need to work with changes as well. And so if you have to do, 6 months worth of legal agreements to work with someone, and then all of a sudden you need to do another 6 months to change to a different group, your project's never going to happen. And so that's kind of why open source is really important. With ML and IoT, both these spaces are in their infancy. We're seeing massive changes in ML pretty much every month. And we're seeing massive changes in the type of things that are considered IoT and the type of processes and performance available in IoT space. And so like a year from now, both the spaces are going to be totally different. And the only way you can deal with this is by collaborating with lots of people and working together.
Thanks, Tim. So a question to Brian now, because Brian has been collaborating quite a bit with ourselves and Google around open source FPGA tooling. So I'd like to kind of hear you speak about, why your company, kind of went to be the pioneer in vendor-sponsored and vendor-built open source FPGA tooling. How's that helping you? Why is that important? And how do you see it going forward?
Yeah, I think I'll start by saying, why didn't we do it for so long? I think that's also useful. And I think that comes down to a lot of companies are scared to contribute the information that's needed in the open source community to make the tools better, for fear of letting go of things that you think are crown jewels to you or core to you. And we were the same. We were no different than that for years, actually. But I think the turning point for us was when our CTO and I actually went to an OR conference in Bordeaux and realized how state-of-the-art the open source tools were and all of the capabilities that they actually could enable from the silicon point of view. And if you think about an FPGA core, it's basically like an engine in a car, which is neat, but it's completely useless unless you have the chassis, the body, the control, the infotainment, and all those other things. And we realized that a company of our size, if we could tap into that community of open source tools, that engine would actually have a really much better home than if we just kept it captive to ourselves. And so that's why we aligned our roadmap around open source tools, because we felt like the product to the end market, the capabilities to the end market are actually going to be much better. They'll tap into the uses of that. And that's happened. I mean, from the moment that we did start participating in open source, we saw other projects and other engineers come in and actually make the core product better, and better in like weeks, which would be, months or years if we were trying to do it by ourselves. So it really just hammers home the power of open source if you're willing to sort of give up some of the control that you think you need to maintain.
Awesome. So it seems like tools are kind of the key focus of today, and I can see how you all are saying that they're important for making faster and better. And we've been developing a tool called Renode, and all three of you have been involved with it to some extent. It's a simulation framework that is, of course, open source, right? And Kate, I wanted to direct this question to you. How do you see Renode kind of interacting with Zephyr, and how can it make Zephyr development better?
Well, Renode really helps developers when they're wanting to prototype before the silicon is available. And because Zephyr is so well supported in Renode and that ecosystem, it's sort of a natural pairing for any type of new innovation work. to move it forward and to be able to do the experimentation before things are cast. You can prototype it out with the silicon through the FPGA interfaces, as well as with the software, get everything working together, get everything tuned up well, and then have confidence that your final design is going to be performing as you expect. So I think Renode is a very valuable addition to the ecosystem and helps with bringing a full ecosystem, having that full ecosystem around Zephyr. So very much appreciate the efforts that Renode's been doing with us.
We very much appreciate how Zephyr has been kind of playing a key role in getting the word out there, that you can do these kind of things. So Brian, you have actually been enabling your platform, starting with the ESS3, but now kind of also going forward with the new platform in Renode. So can you tell me perhaps a bit more about what this ability to simulate your software gives you, and perhaps a little bit about like how you see the workflows in this space with kind of simulation, co-simulation. Here you go.
Yeah, I think if we just start with our current platform, I think, this recent pandemic has actually taught us that it's nice if you can actually have access to tools wherever you are. You don't have to go to a lab. So I think the fact that Renode allows you to do those things anywhere you are in the world, to pretend like you were doing work on the actual chip, I think is a great capability. It's helping that workflow. Moving forward, if we think about the classic way of getting a new chip into the market, into the hands of engineers, we do our own chip design and simulation and tape out and manufacturing and validation, and then we get something out to the end customer. That's a serial process. And a lot of times the software people that need access to the devices to do their software development don't get that capability for far too long. With Renode, we see that as a way of taking out a serial process and making it more parallel. So you can actually push back upstream the capability for the software engineers to start writing code, which has to be written for end products to be deployed. And so why not? I think that's an amazing capability. And it also makes us more comfortable that we can write applications on something that hasn't taped out yet. So we can sort of do system-proof emulation of products before we make the very expensive choice to push the tape out button. So I think it's a great tool for enabling those things. Awesome.
So over to Tim. You guys have been funding quite a bit of Renode development and some very interesting use cases around CI and machine learning. Can you perhaps tell us a little bit about that work and kind of what's in store for the coming months?
Sure. So I think, as Brian said, one of the really important things is doing things with real-world objects is expensive and time-consuming and hard to replicate. And so Renode is really interesting, and it gives you the ability to do a lot of this work without ever having to have any hardware. This makes it super powerful for doing testing. You can have continuous integration systems which run very comprehensive test suites without having to set up very bespoke hardware CI systems. You can use them on traditional CI software systems like Travis or GitHub Actions. And in fact, some of the recent integrations with those tooling has enabled significantly more insight into when things are failing and what they're failing. A really cool example I saw of this is when something fails, Renode can save the complete state of your system and provide it as an artifact which the developer can download and start debugging. And so this gives a power that is very hard to see in hardware. As well, it's significantly faster to change a configuration in the Renode simulator. If you need all of a sudden twice the memory temporarily, you can just change one line in a config file and all of a sudden your hardware has twice the memory. And this can be super useful when trying to debug something or find out what's going wrong is quickly, well, let's enable a whole bunch of debugging, which means it no longer fits on the hardware, but I can make the hardware temporarily better. And lastly, a lot of the things we've been exploring is co-simulation with Renode. This is where, coming back to like the FPGA space, you have a CPU interacting with some type of RTL running on an FPGA. Being able to run your RTL in a simulator like Verilator and hook that up to Renode is quite an interesting facility, because simulating Verilog is very, very slow. So if you have to simulate the full CPU and all the peripherals and everything all together, then your simulation takes a significant amount of time. By instead only simulating the little bit of peripheral and the rest being emulated by Renode, the performance of the test can be significantly faster. And this is particularly important in things like ML, where the ML accelerator is likely to be a little bit of custom RTL, and you want to be able to simulate that, but you also want to change it really quickly. So spending the time developing software, like software emulation exactly of the RTL, isn't quite the right trade-off at that time until the ML kind of accelerator has a more stable interface. And so being able to just use the same code that is running in the FPGA, or even more cool, actually have the peripheral running on an FPGA and using some of the bridge infrastructure we've been exploring, where you basically bridge over things like USB, Ethernet, or PCI Express, enables you to really debug and iterate significantly faster than if you had to do everything directly on hardware, or have to make a choice about how you do your simulation or emulation up front. And it also enables very much the ability to test on lots of different solutions. Renode supports RISC-V, of course, but it also supports ARM and Power. And so you can test on a whole wide variety of different microcontrollers at the same time, which is very important when doing things like TinyML Micro, where you want to be able to test your software across a wide range of devices, and there's only so much disk space. You can't fit that many devices on your desk. And even if you could, not everybody can. So having something like Renode really helps there in making sure you have very good test coverage. I think that's obviously very important for groups like Zephyr as well, which are trying to have this wide support.
Well, that and the fact that we're trying to do a lot of work with testing and making sure the code base stays at a high quality, and being able to work in an emulation environment is, and being able to do a lot of the testing in this way makes it more accessible to a lot of people, rather than just having a certain device on your desktop, as you say. So having these capabilities is what helps, make that quality level higher. And basically bugs happen in hardware too, not just in software. And so being able to debug both of them at the same time is a useful thing, and to figure out where the actual problems are. And as you're evolving new systems and new technologies, you need these capabilities.
And you can put checks in your simulator that you can't put in hardware. It's very hard, for example, to put a check that dumps the complete memory and checks that the memory contents is equal to something if it's encrypted memory or something like that. And so you can do a lot more things and have a lot more debugging. You can have very detailed logging about what was accessed and when what was accessed. And these can exist in hardware, but they're frequently quite expensive to implement in hardware. And so if you can get away without them, your hardware is cheaper, which in the IoT space is a big point, right? Like being able to save on hardware costs really is important when you're going to deploy 1 million of something.
Indeed. Indeed, and that's why you want to have an operating system to complement it, so it's minimal footprint, and you only need what you're only enabling and only running what you actually need. You can configure it to the minimum you need for production, but you can also have an environment where you can do all the debugging before you go to production.
Okay, thanks guys. It's a really good discussion. We're kind of slowly running out of time, so I'll transition to the last round of questions here. I wanted to start with Brian, perhaps, because he's been silent for the last few minutes, and for him to tell us a little bit about kind of what's in store, some kind of closing remarks on Quicklogics and FPGAs, kind of what you guys are looking out for and what you want to enable in the future, and what you're hoping to achieve with all this.
Yeah, well, quite simply, we want to enable more people to use programmable logic at the edge, at the sensor that's putting out data, and do basic computation on that with ML, with AI at extremely low power. So I'd love to see a little programmable logic everywhere, be that in our devices, be that in our FPGA cores that are in other people's devices. And we know that the only way of really achieving that is going to be to make hardware more like software, more appealing and easy to use from the software engineering point of view, as Tim was alluding to earlier. And so all of these pieces with open source software, open source hardware, RISC-V, they're all stacking up the capabilities to go and do that and achieve that vision. And we're incredibly excited about what this next generation platform from us is going to enable in that line of thinking. So yeah, if you're interested in that, then let's talk. But this is really exciting times for us. And next year, I think, is going to be a fantastic year for enabling that capability.
Awesome. Waiting for it. Kate, perhaps you could tell us a little bit about kind of Zephyr and how it fits to all of this, and especially kind of what you're looking out to, what you're hoping for, and what you're hoping to achieve in 2021.
Well, Zephyr is hoping to achieve in 2021. We're going to be going after safety certification so we can be used in some more of the critical infrastructure types of projects for the sensors there. And so we can actually have a coherent solution for this type of technology. And right now we've got a good backlog of the RISC-V patches, and we're looking at bringing in more co-maintainers to help work on that ecosystem so we can accept them quicker. So the word I'll leave you with is, patches for new RISC-V platforms are welcome in Zephyr.
Okay. Tim, any interesting stuff to look out for, and anything else you wanted to say just to close our panel today?
I think we're only just getting started here. I definitely think that there is a lot of interesting things coming, and we're going to see the pace of innovation pick up. And so if you're already struggling with how fast things are moving in this space, you might want to try adapting sooner because it's only going to get worse. Things are only going to continue to change faster, and they're only going to continue to change under you faster as well. So I think we're definitely going to need a lot more FPGA because, protocols and ways of solving problems are going to appear faster than ASIC people can tape out and verify them. And we're going to need to iterate on them significantly faster because a lot of them are going to have ways to improve them that are to specific applications. Some groups will want a configuration in one way, and some groups will want a configuration other way, and you won't be able to serve both while still hitting your budget if you don't do a reconfigurable solution. And all that's going to have to be backed with lots and lots of software to make it work. And so definitely we're going to need a lot more work on things like Zephyr. We're going to need a lot more work on things like RISC-V. I definitely think we didn't even mention things like the fact RISC-V is enabled to add custom instructions. Supporting that in software and in FPGAs is a complex task, but can offer significant improvements to your performance, especially if you spend most of your time doing one thing. Converting that thing to a single operation in your CPU has significant advantages. And this is kind of why all these pieces are important to the ecosystem and why they all need to be open accessible to anyone, because we don't know who's going to come up with the next great solution to this, or rediscover something from the 1980s that was dismissed as never going to be useful that actually turns out to be fundamental to
like deep learning
in the future, like machine learning.
Yeah.
So, yeah.
Absolutely. Thank you very much. We're running out of time now, so I wanted to just extend my thanks to all of you. I'm Michael Geilda, by the way. I forgot to introduce myself at the very beginning. And today I had Brad Faith, Kate Stewart, and Tim Mansell talking about machine learning and IoT, RISC-V Zephyr, and Renode. I hope you enjoyed the panel and looking forward to your questions. Thank you very much. Goodbye.
Thank you.